Right, so we're going to talk about gases, start our unit on gases and solutions today. And the first thing that we need to understand about gases are just some basic properties. So we're talking about a sample of a gas in a container, in a balloon, whatever the sample may be. What are some things that we might be able to measure? First, though, let's talk about what makes gases unique. There you see a little picture here of a solid, a liquid, and a gas. You can kind of see a lot from this picture. The solid is very organized in kind of a crystal structure. The liquid is still pretty close together. The particles are pretty close together, but a lot less organized, and you can see it's kind of like taking the shape of its container, whereas the solid has its own shape. And then over here, our gas, the particles are very spread out, very sort of disorganized, disordered, and they're filling up their entire container. So the three most common states of matter, solid, liquid, and gas, we're not going to talk about plasmas, but of those three, gases, we can say have the most kinetic energy of the three. So they're moving around the most. And they also have the smallest intermolecular forces. So, for example, in my solid, liquid, and gas up here, let's say these are three different substances at the same temperature. The solid might be sodium chloride, like an ionic compound, and so those are ionic bonds holding them together. The liquid might be water, and so that's like hydrogen bonding or dipole-dipole forces holding them together. And the gases may only have slight attractions, like London dispersion forces. And they also might be very small particles, which means that, again, at that given temperature, they're going to be more spread out and, apart from one another. So the fact that they have smaller intermolecular forces is going to lead to them being more likely to be a gas at a given temperature. It also makes them, of the three states of matter, have the least or the smallest density, which should make sense because the particles are spread out, right? So they take up a lot of volume, even though they may not have a lot of mass. Okay, 4 variables we're going to be looking at. Number 1, the volume of a gas sample can be measured in liters or milliliters. We could use gallons or, pints or whatever, but in chemistry we use liters or milliliters. And because of their high kinetic energy, that gas is always going to occupy its entire container. And so we can say the volume of the gas equals the volume of the container. So it makes finding the volume of a gas often pretty easy. So, for example, let's say I have a water bottle that has 300 milliliters of water at the bottom, and then above that it has a sample of gas, right? Let's say that the total volume of the entire bottle is let's say 1,000 milliliters. Well, that means we can assume that the gas sample has a volume of 700 milliliters. Also keep in mind though, because gases do expand to fill their entire container, this 1,000 milliliters would have to include even this tiny little space up here near the cap. So unlike a water bottle where it would just have a little marking on the side, and that's how you would read the volume, a gas will actually expand to, of course, fill the entire container, even the very top up to the cap. Okay, so that makes volume pretty easy to measure. Another thing that we can measure about a gas is its temperature. Temperature is usually going to be measured in kelvins. We may sometimes take the measurement in Celsius and then change it to kelvins. So kelvins are just a measure of temperature. Kelvins are degrees Celsius plus 273. So for example, if the temperature of the room equals 25 degrees Celsius, that would be equal to 273 plus 25, so that would be 298 kelvins. And kelvins are unique, and the reason we use kelvins in talking about gases and gas laws is that they are absolute. So they describe the movement of the particles, whereas the Celsius scale is relative. 0 Celsius equals the temperature of freezing water, so it's the freezing point of water. But water molecules are still moving at 0 degrees Celsius, and so are the air molecules around them. So 0 kelvins are unique because 0 Kelvin is the theoretical temperature where all particles would completely stop moving. So at 1 Kelvin, the particles are still moving a little bit, but at 1 degree Celsius, they're moving a lot, right? And at 0 degrees Celsius even, they're moving a lot. So Kelvin is absolute, and so you'll never have a negative Kelvin temperature. So what is temperature in the first place, though? Temperature is defined as the average kinetic energy of particles in a sample. Another thing that we want to note here is that kinetic energy, when we say kinetic energy is equal to 1/2 mass times velocity squared. So what does that mean? Well, if temperature is a measure of average kinetic energy, then it's not just how fast the particles are moving, it also has to do with their size. So at a given temperature, and I'll show you here from a little PhET demonstration, at a given temperature, I'll put some large particles into this little box with this little bicycle pump, and then I'll put some small particles in there. Now they all have the same temperature. You can see there it's 300 kelvins. But the little red guys, which are smaller, are moving around a lot faster. And that's because even though everything in this box, or I should say on average, everything in this box is at the same temperature regardless of size, the larger particles are moving slower in order to have the same kinetic energy. Okay, so the small particles moving really, really fast, the large particles moving really, really slow, but they both have the same average kinetic energy. And we'll get into that a little bit more throughout the unit, but just understand that kinetic energy isn't just how fast stuff is moving, it also has to do with size. Not going to spend a whole lot of time talking about number of particles or moles. You already kind of know what that is. It's just basically counting up particles. But that is something that we can express about a sample of a gas. How much of it is there? It is also important to note that the symbol for number of moles is a lowercase n. Pressure, which is symbolized by P, is just a force over an area. So for example, if you wanted to cut a steak, so let's say this little slab of steak here, and you have a dull knife, so the edge of it is kind of rounded if you look in close. As you apply force, right, force is in the numerator, because the area is so big, because the area is large and it's down there in the denominator, the pressure created by this dull steak knife is too small to cut the steak. Okay, unless we also increase the force and push down with a lot of force, then we can get enough pressure to cut it. If you sharpen the knife, what you're doing there is you're decreasing the surface area that's coming into contact with the steak. So as that goes down, even without increasing the force a whole lot, you can increase the pressure, right? So pressure is created by a force applied over an area. In a gas sample, it's going to look a little different. You're going to have trillions and trillions of interactions. So let's say you have a balloon here and a bunch of gas particles inside of that balloon. You're going to have trillions and trillions of interactions of these gas particles with each other, but also with the walls of their container, right? And so that's what creates gas pressure. Gas pressure results from collisions of gas particles with the wall or walls of the container. Okay, there's a couple different ways to measure it. We can measure pressure in pounds per square inch, PSI, so how much force is applied over a certain area. ATM, which is atmospheres, kilopascals, kPa, or we can also measure it in millimeters of mercury, which is the same thing as torr. Now, I know all of this stuff doesn't mean a whole lot to you right now, but as we get into this and explain what each of these units, is at standard sea level, hopefully it'll make some sense. So PSI, even though we don't use PSI a whole lot in this class, but we use it for like tires and basketballs and stuff like that. So it might be something you're familiar with. This little drawing is explaining this to you. So if you had a column of air, just regular atmospheric air, that was 1 inch squared and extended all the way up into the air, into the ionosphere, so basically the edge of the atmosphere, the mass of the air in that little 1 inch by 1 inch tube is going to weigh 14.7 pounds. So it's going to go, I don't know, something like 60 or 70 miles into the atmosphere. But it's only going to be 1 inch by 1 inch squared. So it's going to weigh 14.7 pounds. So what that means is for every square inch a surface here on Earth is feeling from atmospheric pressure, from atmospheric air, there are 14.7 pounds of force pushing down. So standard sea level atmospheric pressure is 14.7 pounds per square inch. Okay? And again, sea level is a little different. If you're up in the mountains, of course, it's going to go down. If you're way down deep in a valley that's below sea level, it would even be greater than 14.7 because there would be more air, right? Okay, we more likely use atmospheres. That's going to be one that we commonly use. And so in atmospheres, standard pressure at sea level is 1 atm. And then in kPa, it's 101.3. So these numbers are all equal to each other, just like saying 1 foot equals 12 inches. All of these numbers are equal to each other because we're changing the units. And then if we are in millimeters of mercury, which is synonymous with torr, the number is 760. So if we do a problem like this one, a car tire is supposed to be inflated to 240 kPa. How many atmospheres is this? Well, I just do it like a unit conversion. kPa on the bottom, atmospheres on top. 1 atmosphere equals 101.3 kPa. And so 240 divided by 101.3, round for 2 sig figs, should give me about 2.4 atmospheres, or about 2.5 times normal pressure that we are used to feeling from the atmosphere. The way this is measured, atmospheric pressure is measured, is using a barometer. So here you can see this is liquid mercury in a dish that's open to the atmosphere, and then you have an evacuated glass tube that is filled with mercury and then turned upside down. At a normal day, weather-wise, at sea level, the force of the atmosphere pushing down out here, which is represented by the blue arrow, can support 760 millimeters of that liquid mercury. And so that's how we measure pressure.